Hello everyone. In this video, we're going to talk about how to find the power series representations of certain functions. Recall that up until now, we really only know how to actually compute the sum of one kind of series, geometric series. We have a formula that tells us that the sum of a geometric series is the first term over 1 minus the common ratio. And this formula works if the absolute value of the common ratio is less than 1. If we think about the right-hand side of this equation as a function of r, it turns out that this equation actually gives us the power series of that function. More precisely, if we let g of x be the function 1 over 1 minus x, then the geometric series formula tells us that this function is equal to the sum from n equals 0 to infinity of x to the n. And this formula is valid when the absolute value of x is less than 1. And so we've done it. We found the power series representation of a function. Before we move on, I just want to take a quick minute to explain why this may be a worthwhile thing to do. Just like we saw before for regular series, the partial sums of the power series, which look like 1 plus x squared all the way to x to the n, provide good approximations for the function 1 over 1 minus x on the interval minus 1 to 1. This can be helpful because the partial sums are one of our favorite types of functions, polynomials. We like polynomials because they're very easy to deal with in a calculus setting. In particular, they're very easy to differentiate and integrate. So, the point is that we can approximate the function we're given by polynomials. Moreover, if we take further partial sums, we get a better approximation for the function in the interval. We'll talk about how to quantify the accuracy in these approximations when we look at Taylor series later on. So that's one of the reasons why power series are useful. They provide simple approximations to complicated functions. Because, like we said, they're very easy to differentiate and integrate. And one more reason that is less relevant for our purposes, but you may come across if you take more calculus classes, is that the power series representation can be useful when trying to solve differential equations. Okay, hopefully by now I've convinced you that finding power series representations is actually a reasonable thing to do. So, our goal for the remainder of the lecture is going to be to find power series representations of other functions. The first method that we're going to use to find other power series representations is substitution. What I mean by substitution is, if we're given a function that looks similar to 1 over 1 minus x, but the x is replaced by something else, we can substitute that value in for x in the power series for 1 over 1 minus x. So, for example, let's say we have the function 1 over 1 plus x to the 7th. This function looks almost exactly like 1 over 1 minus x, but the x has been replaced by minus x to the 7th. So we just plug minus x to the 7th in for x in the power series for 1 over 1 minus x to get the sum from n equals 0 to infinity of minus x to the 7th, all to the nth. And this representation is valid when the absolute value of minus x to the 7th is less than 1, which is the same thing as saying that the absolute value of x is less than 1. Finally, we can simplify this to get the sum of minus 1 to the n times x to the 7n. And that's how substitution is going to work in general. Let's do a couple more examples. Consider the function 2x over 1 plus x. Our first step is going to try and make this look like 1 over 1 minus something. The first thing we can do is pull the 2x off the top, and then we're left with 1 over 1 plus x, which we can rewrite as 1 over 1 minus negative x. Now we can rewrite the 1 over 1 minus negative x as a power series to get 2x times the sum from n equals 0 to infinity of minus x to the n. And this power series representation is valid when the absolute value of minus x is less than 1, which is the same as the absolute value of x is less than 1. Next, we can pull apart the minus 1 to the n and the x to the n, and then multiply the 2x inside the series to get the sum of 2 times minus 1 to the n times x to the n plus 1. As a final example, consider the function 1 over 4 minus x. Again, our first step is writing the function as 1 over 1 minus something. So Our only problem with the current function is the 4. Let's pull a 4 out of the bottom to get 1/4 times 1 over 1 minus x over 4. Now we can write the 1 over 1 minus x over 4 as a power series to get 1/4 times the sum from n equals 0 to infinity of x over 4 to the n. And this power series representation is valid when the absolute value of x over 4 is less than 1, or the absolute value of x is less than 4. Finally, we can clean up the series by splitting apart the x to the n and the 4 to the n, and multiply the 1/4 inside to get the sum of x to the n over 4 to the n plus 1. And there you have it. This is one way that we can get a new power series representation from the one that we know. The other method that we're going to use to get new power series representations is by differentiating and integrating ones that we already know. For example, let's start with our good old 1 over 1 minus x equals the sum from n equals 0 to infinity of x to the n, where x is between minus 1 and 1. If we differentiate both sides of this equation, we get 1 over 1 minus x squared on the left, and on the right, we can just differentiate term by term. Remember, we're differentiating with respect to x, so we treat the n's just like constants. So this is just like differentiating a polynomial. We bring down the exponent, and then lower the exponent by 1. Now, we should be a little careful here. The first term of the original series, that is, the n equals 0 term, is 1, which is a constant. Therefore, when we differentiate, this term should go away. However, in the series we got, the n equals 0 term has an x to the minus 1 in it, which probably shouldn't be there. So the way we compensate for that is by raising the starting index of the series to 1. This is going to happen every single time you try to differentiate a power series that has a constant term in it. And so, now we have found the power series representation of 1 over 1 minus x squared by differentiating. We can do a similar thing by integrating. Let's start with our power series representation of 1 over 1 minus x. And we can integrate to get minus natural log of 1 minus x plus c on the left, and we integrate term by term on the right. The exponent goes up by 1, and then we divide by the new exponent. Something a little strange happens in this case. It turns out that this power series representation is valid for x between -1 and 1, but including -1. This is because the series that we got when we integrated actually converges at x equals -1, even though the series that we started with does not. This is something that can happen in general. In particular, it's possible for the convergence or divergence of a series to change at the endpoints of the interval when we take the derivatives or integrals. This is just something to keep in mind when you're using this method. So, we're almost done. The only thing we need to figure out is the value of c, and we do that the same way we always have, by plugging in a value for x. Technically, any value of x in the interval would work. However, we want to plug in x equals 0, since this will make all of the terms in the series vanish, and we can get an actual numerical value for c. When we plug in x equals 0, we get minus natural log of 1 plus c is equal to 0. And we need to be a little bit careful here. If the series had a constant term, then not all of the terms would vanish when we plug in 0. However, since the exponent on the x is n plus 1, we see that the power of x is always at least 1, and so there are no constant terms in the series. Finally, we can solve this equation to get that c is equal to 0. And so, we conclude that the power series representation for a natural log of 1 minus x is minus the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1. Now, right now is probably a good point to take a step back and fill in a gap that we talked about a while ago. When we talked about alternating series, we discussed the sum from n equals 1 to infinity of minus 1 to the n over n. This series was interesting because it converges, but it does not absolutely converge. In other words, it's conditionally convergent. We then proceeded to estimate the sum using the alternating series estimation theorem. However, we know enough now to actually compute the sum. Let's go ahead and do that. We need to start by doing a little series magic to make the series look like one of the series we just talked about a second ago. Notice that all of the series we have dealt with in this video have started at n equals 0, but this one starts at n equals 1. It turns out we can make this series start at n equals 0 using a process called reindexing. Now that's a scary word, but the idea is not so complicated. Let's go ahead and write out the first few terms of the series. We have minus 1 over 1, plus 1 over 2, plus minus 1 over 3, plus 1 over 4, and so on. Now, with the indexing that we were given, minus 1 over 1 is the term corresponding to n equals 1, 1 over 2 is the n equals 2 term, minus 1 over 3 is the n equals 3 term, and so on. However, we want to start the series at n equals 0. So let's change it so that minus 1 over 1 is now the n equals 0 term, and 1 over 2 is the n equals 1 term, and minus 1 over 3 is the n equals 2 term, and so on. Now, with this indexing, we see that we can rewrite the series as the sum from n equals 0 to infinity of, well, the numerators are alternating, and so we get a minus 1 to the n plus 1 to make the signs go in the right order, and the denominators are just one more than the index, and so n plus 1. And so we have reindexed our series starting at n equals 1 into a series starting at n equals 0. Now, notice that this series looks very similar to a series we saw earlier. Recall, we found that the power series representation of natural log of 1 minus x is minus the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1. The power series we got is exactly the power series showing up in this formula, just with a minus 1 plugged in for x. Therefore, this sum is equal to negative natural log of 1 minus negative 1, which is equal to negative natural log of 2. And so we've computed the actual sum. For a final example, I want to compute the power series representation of one more function, and that function is inverse tangent. We're going to do this just like we did before, by relating inverse tangent to a function that looks like 1 over 1 minus something. Going through what we know about inverse tangent, we see that the derivative is equal to 1 over 1 plus x squared, which is pretty close to the form that we want. We can rewrite this to get 1 over 1 minus negative x squared, and now we see that the power series of this function is the sum from n equals 0 to infinity of minus x squared to the n. And this power series representation is valid when the absolute value of minus x squared is less than 1, or the absolute value of x is less than 1. Now we can simplify a little bit to get the sum of minus 1 to the n over x to the 2n. So we have found the power series representation of the derivative of the function we want. Therefore, in order to find the power series for the inverse tangent function, we integrate this power series to get the sum from n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1. And then we have to throw a plus c in there because we integrated. So, to finish it off, we just need to find the c. Just like before, we plug in x equals 0 and get that inverse tangent of 0 is equal to c plus 0. Again, we have to be careful here that the power series does not have a constant term. And so we find that c is equal to 0. So the power series representation of inverse tangent is equal to the sum from n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1. And this representation is valid for x in between minus 1 and 1. As a final note, it turns out that the interval actually contains both negative 1 and 1, since the series converges at both of these values. Alright everyone, that's all I have for today. I'll see you next time, and have a great rest of your day.